Today we will study about enzyme kinetics. Enzyme kinetics is the study of the chemical reactions that are catalyzed by the enzymes. In enzyme kinetics, the reaction rate is measured and the effects of the varying the condition of the reactions are investigated. So, it is a quantitative measurement of the rate of the enzyme catalyzed reactions. It began in 1902 when Adrena Brown reported an investigation of the rate of hydrolysis of sucrose. According to the Brown demonstration, when sucrose concentration is much higher than that of enzyme, reaction rate become independent of the sucrose concentrations. Here it is the mechanism of the enzymes action, means enzymes plus substrate gives enzyme substrate complex, and it is a reversible reaction, means further it can be broken down into enzyme and substrate or can be broken down into product and enzymes. Here K1 K2 are the forward reaction rates and K minus 1 is the backward reaction rate. According to the Brown proposal, overall reaction is composed of two elementary reactions in which substrate form a complex with the enzymes that decomposes to the products and enzymes. So, we can say that the velocity or the rate of reaction can be given by time rate of change of product is equals to K2 into ES. The overall reaction rate becomes insensitive to the further increase in substrate concentration, means once attaining at a limited value, there is no further change in the rate of reactions. So, the overall rate of production of enzyme substrate complex, the difference between the rate of elementary reaction leading to its appearance and its disappearance. Enzyme plus substrate, that is enzyme substrate complex, and further broken down into product and enzyme. So, the equations here is time rate of change of enzyme substrate is equals to K1 E into S minus K minus 1 ES minus K2 ES. So, this equations must be solved by taking some assumption, the rapid equilibrium assumption that leads to Michaelis-Menten approach, and the steady state assumptions that lead to Haldane approach. So, we will see how we will derive these equations by using some assumptions. Let's start with the Michaelis-Menten approach. Here we will consider that rate of initially the rate of formation of enzyme substrate complex is equals to deformation of enzymes and substrate. So we can say that K1 E into S is equals to K minus 1 ES. So we can rewrite this equation K minus 1 upon K1 is equals to E into S upon ES. If we denote K minus 1 upon K1 as Km, that is the equilibrium constant Km. Again here we will utilize the conservation equations that the enzyme is not consumed. Here the total enzyme is given by E naught is equals to free enzyme E plus enzyme involved in substrate formation. From this we can get free enzymes is equals to total enzyme minus enzyme substrate complex. So the equation we get is in this form, that is Km is equals to E into S upon ES. If we replace E by E naught minus ES, we will get the equation that ES is equals to E naught minus ES into whole S upon Km. By solving this equation, we will get by putting Km on the left side, we get ES Km is equals to E naught into S minus ES to S. So, rewriting this equation, we will get in the terms of ES is equals to E naught into S upon Km plus S. Again, if we in the previous equation, if we multiply both sides by K2, we will get the equation in the form like K2ES is equals to K2E0 into S upon Km plus S. Earlier we defined that is the rate of reaction is given by time rate of change of product, that is equals to K2ES. So we can write rate of reaction V is equals to K2E0 into S upon Km plus S. If where V max, that is K2 is into E naught is V max, by putting this value in the equation, V equals to V max into S upon Km plus S. This is the Michaelis-Menten equation. Now some steady state assumption is also done, while the Haldane further modify this equation. From the graph we can see with the changing time the concentration of substrate decreases while the concentration of product increases. Hence synthesis of enzyme substrate complex must be equals to its consumption over the course of reaction. So by taking again the mechanism of enzyme substrate, E plus F gives ES and further E plus P, here P is the product. Now taking the steady state assumption, that is time rate of change of enzyme substrate complex is equals to 0, we can write time rate of change of enzyme substrate complex is equals to K1 into E into S minus K minus 1 ES minus K2 ES is equals to 0. By solving this equation we will get ES is equals to E into S K1 upon K minus 1 plus K2. Here we define Km as a Michaelis constant, that is Km is equals to K minus 1 plus K2 upon K1. So substituting the value of E equals to E naught minus ES in the Km, we will get the equation in the term of Km equals to E naught minus ES into S upon ES. By solving this equation, we will get the equation in the term of ES, that is E naught into S upon Km plus S. Again using the same concept as the rate of product formation can be expressed in the term of S, we can write V equals to time rate of change of product is equals to K2 into ES or K2 E naught into S upon Km plus S, or K2 E naught is equals to V max. So the final equation we get is rate of reaction V is equals to V max into S upon Km plus S. So what is V max and what is Km? We have to define this. We can say that Michaelis-Menten equation is a statement of the quantitative relationship between the initial velocity V naught, the maximum velocity V max, and the initial substrate concentration S. One more thing is here, that we can write initial rate, that is V naught, is exactly half of the maximum rate. So let's define Km. Km is the substrate concentration required to reach half the maximum velocity, means Vmax upon 2. Km is a measure of a substrate affinity for the enzymes and the Vmax. Considering the total enzyme concentration, the maximal rate that the enzyme can attain is Vmax. So we can say Vmax is equal to the product of the catalytic rate constant and the concentration of the enzyme. Here is some features of Michaelis-Menten reaction, like assumes that enzyme substrate complex is in rapid equilibrium with free enzymes. Breakdown of ES to form product assumed to be slower than formation of ES and breakdown of ES to reform enzyme and substrate. Here we define another term, that is Kd. It is a equilibrium dissociation constant. Kd is given by Kd equals to enzyme into substrate upon enzyme substrate complex. With the help of Michaelis-Menten equation, we cannot easily plot the graph between Km and Vmax. So we can do this by using some other equation, that is given by Lineweaver work equation. So it is called Lineweaver work equation. So, in this, by taking the reciprocal of the Michaelis-Menten equation, we get 1 upon V naught is equals to Km upon V max into 1 upon S plus 1 upon V max. If we compare this equation, it is a equation of a straight line. Here y is equals to ax, and here y is equals to 1 upon V naught, Km plus Vx is A, and 1 upon V max is B, while 1 upon S is X. So, if we plot the graph is plotted between 1 upon V naught as a y function of 1 by S, as their x therefore gives a straight line whose intercept is 1 upon V max, from the view whose y intercept is given as 1 upon V max, and slope is given by here Km upon V max. This graph is also called double reciprocal graph or Line-Weaver-Burk plot. Line-Weaver-Burk plot has the great advantage of allowing a more accurate determination of Vmax, which can be only approximated from a simple plot of V naught, means initial reaction rate versus substrate. So, this double reciprocal plot of enzyme reaction rate is very useful in distinguishing between certain type of enzymatic or reaction mechanism.